Welcome, this is Dr. Plague, and this is part 2 of designing a clock source for homemade CPUs. So, in the last video I designed a single-step source that used a tactile switch to toggle the clock signal. I also developed a switch debounce circuit in that video. Now, I want to add in another switch, the run-stop switch. This switch will be used to either allow or disallow a running clock source to get through to the clock signal. There are many ways we could design this, but I'll just look at a few of them. I'll just connect up a second switch to another debounce circuit using the Schmitt-Trigger inverter on pins 11 and 10 on the 74HCT14. Now, pin 10 of the 74HCT14 will be the output from our second debounced switch. Let's label these switches so we know what each one is for. Now, let's go to DigitalWorks and design this second switch into our current circuit that we left off with. I'll just label this switch as run stop, and then label the first switch as single step. I'm going to use the second D flip-flop in the 7474 to create the same circuit as our first switch. What I want for the second switch is to toggle another output from the D flip-flop. I'll connect the switch to the clock input of the second D flip-flop. Then I'll tie the preset and clear pins high to disable those. Just like with the first D flip-flop, I'll connect the inverted output up to the data input. And I'll just add in an LED right here to test this out. Now both switches work identically with their own LEDs. Perfect. Let's add this to the breadboard and make sure it works. Instead of connecting the clear input to VCC, I'll just connect it to the clear pin of the first flip-flop. That way the second flip-flop always starts up in the clear condition. I'll keep preset connected to VCC and connect the inverted output to the data input. Then I'll connect the switch output to the clock input of the flip-flop. And I'll place the LED way over here as an indicator of whether we are in the run or stop state. Ultimately, when the LED is lit up, then we'll be in the run state. And if it's unlit, then we can use the single-step switch. Here's the current limiting resistor from the LED to ground. Let's power this up and test it out. And it's working perfectly. Great, let's continue. I'll add in this clock signal to represent the running clock source in our circuit. Now, I want either the single-step switch or the running clock source to get through to the clock input of the D flip-flop. So I'll just add in an OR gate right here. The problem with this is that we can't keep the running clock source from getting to the flip-flop so that we can use just the single-step switch. The second switch is supposed to choose between the running clock source or the single-step switch. So I'll just send the running clock signal through an AND gate like this. Then I'll connect the flip-flop output from the run-stop switch to the other input of the AND gate. Now, when this run-stop LED is lit up, we'll be sending a high to the AND gate here, which will allow the running clock source to get through. And when the LED is not lit up, we'll be sending a low to the AND gate here, which will now output a low regardless of the level from the running clock. So this run-stop switch will either allow the running clock source to get through or disallow it from getting through. The single-step switch can get through at any time though, which is fine with me. Also, notice that this method divides the frequency of the incoming clock source by 2, and I'll talk more about that later. What I don't like about this is that it would require 2 additional ICs, one for the AND gate and one for the OR gate. Let's see if we can find a way to use just one IC. Now, we could use something obscure, such as a single 3-input positive AND OR gate. Beautiful. But this isn't something that most people are likely to have in their collection. So let's find an alternate solution. Let's look at this OR gate. There's only one way we can get a low output from it. Both inputs would need to be low. For an AND gate, both inputs need to be high to get a high output. What if we invert both inputs to an AND gate? Then the only way we can get a high is to provide a low on both inputs. Then all we need to do is invert the output of this AND gate like this. Now we have a NAND gate with inverted inputs. This will work the same as an OR gate. So let's replace this OR gate with this inverted input NAND gate. Now let's just move this inverting dot to the output of this AND gate. We now have 2 NAND gates with one inverting input on this NAND gate. We can pull this inverting dot out to here and use an inverter. So now we have 2 NAND gates and 1 inverter. But we can replace this inverter with another NAND gate and just tie the inputs together like this. So this new circuit should function the same as the AND and OR gate that we started with. And now we can use a single quad 2-input NAND IC, which would be the 7400. Let's change the circuit in DigitalWorks to match this. Okay, let's test this out. And it functions the same as before. Beautiful! Now, if we wanted to, we could send this inverted output from the second D flip-flop to an input of this AND gate instead of tying both together. This would truly cut off the single-step switch from getting through when the run-stop switch is set to run mode. But, personally, I like it the other way. Now, let's talk a little about the frequency division of the running clock source. There could be many sources for this running clock source, and let's say we're using a 555 timer. The use of a 555 timer would make it fairly difficult to provide a 50% duty cycle. We can probably get close to 50%. But if we just divide the signal by 2, then we get almost exactly 50% duty cycle. So this is one case in which I welcome the frequency division. But what if we're using a source that already has a fairly accurate 50% duty cycle, such as a crystal oscillator, or maybe we're using a waveform generator? In those cases, it might be preferable to not divide the frequency. So I'll look at some ways to avoid the frequency division. But first, let's breadboard up the solution we have so far and demonstrate it. So I'll just add in a 74HCT00 NAND gate right here. I'll add power and ground. I'll use these 3 NAND gates, so I'll tie the unused inputs of this gate high. Then I'll disconnect the debounced single-step switch output from this flip-flop and connect it to both inputs of the first NAND gate. I'll connect the outputs of these 2 NAND gates to the inputs of this NAND gate. Then connect the output of that NAND gate to the clock input of the flip-flop, which is where the debounced single-step switch was previously connected to. Then I'll connect the output of the second flip-flop to one of the inputs of this NAND gate. Now, the other input of this NAND gate can be used for connecting up to the output of whatever running clock source we choose. I'll just add in a 1 MHz crystal oscillator, add power and ground, and connect the output to the NAND gate. Let's connect up some scope probes to this circuit. I want to look at the output from the crystal oscillator on channel 1 and the output from our clock source circuit on channel 2. Now let's power this thing up. And if I turn on the run mode, we get 1 MHz from the oscillator and 500 kHz from the clock source output, which is 1 MHz divided by 2. So we do indeed get a frequency division. Let's trigger on channel 2 instead so we can see both waveforms clearly. There, that looks a little better. Now, there are a number of ways to avoid this division, so let's look at a few of them. What we could do is change the connections of these NAND gates and use them as a mux for the output. Here's how I'll do that. First, I'll disconnect the NAND output to the flip-flop. Then I'll move the output of the debounced single-step switch from the input of this NAND gate to the clock input of the flip-flop. I'll move the connection of the output LED to the output from the NAND gates. And I'll connect the output from the first flip-flop to the input of this NAND gate, where the single-step switch was previously connected. Finally, I'll break up the inputs to this NAND gate and connect the inverted output from the second flip-flop to it like this. Now, we can see the LED flashes with the same frequency as the running clock. And the run-stop switch will select between the running clock and the flip-flop output from the single-step switch. We could also use a conventional MUX IC, such as the 74157. With the 74157, we would only need one line to control the selection, instead of both the inverted and non-inverted outputs from the second flip-flop. So, what this will do is use the signal on pin 1 of the 157 to select which of the two inputs on pins 2 and 3 to send to the output on pin 4. And pin 15 is used to enable the 157, so it needs to be low when enabled. When the signal on pin 1 is low, then the output will copy the signal on pin 2. And when pin 1 is high, the output will copy pin 3. The 157 is a quad MUX chip, so there are 3 more MUXes inside the 157, which all share the same select line, and I'm just using one of them. But what if I don't want to reconfigure the NAND gates to connect directly to the output LED? Let's put this circuit back to the way it was. Since the output of the first flip-flop toggles on the positive going clock pulse, all I need to do is find a way to send a positive going clock pulse each time the input level of the running clock changes. We could use some exclusive OR gates to do this. Let me draw this up for you. First of all, let's say this is the incoming running clock signal. What I want is something like this, where each edge is converted into a positive going clock pulse. So, when the running clock level is low, I want a low signal. I also want a low signal whenever the running clock level is high, but it's the transitions where I want a positive clock pulse. Let's think about how an exclusive OR gate works. If both inputs are low, we get a low output. And likewise, if both inputs are high, we get a low output. We get a low output whenever both inputs are the same. So, we could send the running clock signal into both inputs of the exclusive OR gate like this, and we would expect an output that is always low. We have the majority of the signal we are aiming for. We're just missing the positive pulses at the transitions. Now, what if we can find a way to slightly delay one of the inputs to this exclusive OR gate? Then we would get two signals going into the gate that look like this. Whenever we send different levels to each input of the exclusive OR gate, we get a high on the output. So, if one input is slightly delayed, then we get a low output when both inputs are low, then a high output during this short period where both inputs are opposite, then back to a low, etc. This would work perfectly, but how can we get this slight delay to one of the inputs? Well, if we use a 74 series 86 quad 2-input exclusive OR chip, then we get 3 extra gates. Let's use those gates for their propagation delays. If we just ground one of the inputs to each of those gates, then the output will follow the other input. So I'll connect them up like this. Now, all we need to do is connect these 4 exclusive OR gates between the running clock signal and the input to the NAND gate in our circuit. So, let's do that. I'll disconnect the running clock, add in the exclusive OR gates, connect those to where the running clock was previously connected, and connect the running clock to the input of these new gates. Let's give this a shot. Now, whenever we're in run mode, we can see that the output signal follows the running clock with no frequency division. And single-step mode still works. Perfect. Let's add a 74 HCT86 quad 2-input exclusive OR IC onto the breadboard. And for that, I'll just move this oscillator over here. And let's send the running clock through these exclusive OR gates like I did in the simulation. Time for the test. Here we go. If I put the circuit into run mode, we can see that the frequency of the output now matches the frequency of the 1 MHz crystal oscillator. Beautiful! And I can remove the crystal oscillator and replace it with the output from a waveform generator. and I have it set up for a 5 Hz square wave. And if I send that through, then I get a 5 Hz clock signal output from this circuit. Awesome! So now I'll remove the exclusive OR gates and add in a 555 timer IC. Now, I made a previous video on the 555 timer IC, so I won't go over 555 circuit designs in this video. I'll just show this schematic of the 555 timer circuit that I'll be adding into my clock source circuit. This should produce somewhat close to a 5 Hz signal, depending on tolerances and such, although I will end up making this adjustable. I'm using 10K resistors along with a 10 microfarad capacitor to set the frequency. Let's connect this circuit up. And I'll connect the output from the 555 to the input of the NAND gate right here. Since I'm not going through the exclusive OR gates, the final frequency should be half the frequency coming from the 555. Okay, I'll connect channel 1 of the scope to the output from the 555, and channel 2 to the final clock source signal. Let's power this up and put it into run mode. We can see the frequency from the 555 is about 6.6 Hz and has a duty cycle of about 66%, and the final clock signal has a frequency of about 3.3 Hz, with very close to a 50% duty cycle. Fantastic! And the single step function is still working. Awesome! Now, as I mentioned earlier, I want to make this frequency adjustable. I want a fairly wide range, maybe around 1 Hz to 10 kHz or so. It doesn't need to be exact. I want to use something like this here potentiometer, but this one is only 10K ohms, a fairly small range. In fact, all my breadboardable potentiometers have low values, such as this 5K, 1K, another 1K, 2K. I have some like this that are 5K and 10K. I do have larger valued pots, like these. This one is 1 meg. Or even this slide pot, but they won't press nicely into a breadboard. So these smaller pots won't give us a very large frequency range when using them with the standard 555 circuit configuration. Sure, I could buy some larger values, but even with, let's say, a 1 megohm pot, we probably would have a hard time getting a range from 1 Hz to 10 kHz. So we need to think outside the box. Since this video is getting lengthy, I'll tackle this problem in part 3. So, in part 3, I'll show you how I plan on using a 10K potentiometer to create an adjustable frequency range from around 1 Hz to 10 kHz. And actually, the range will need to get up to about 20 kHz, since my clock source circuitry will divide that by 2. So, be sure to tune in to my next video to see how I plan on accomplishing this. Well, now I'm close to being all set with a clock source circuit to use on any of my future homemade CPUs. I just want to add in some adjustability to the frequency. Now, granted, there are many ways I could have made a clock source. And if you're designing a clock source circuit, I encourage you to do some experimenting. Design it the way that you like it. You don't need to copy any of my designs. You could do something completely different. I'm just showing my design as a starting point. Be creative and make it your own. Most of all, have fun with your designs. And that's all I have for this video. Thanks for watching, and I'll see you next time in part 3, right here on Dr. Play.